All right, so it's time. Welcome to the Applied Math Seminar. Today we have Navid in our department to talk about meta-learning, biologically plausible plasticity rules. You're learning the rules, right? That's great. And
Thank you so much. Thank you so much, everyone. Welcome. Hope you're having an amazing day. So today I'm going to talk. So I'm a postdoc here in a computational neuroscience lab. What I'm working on is essentially artificial neural network and their learning rules, also known as plasticity rules. And in this project that I'm going to talk about, we used a machine learning paradigm called meta-learning to learn these learning rules under some biological constraints. So a quick intro on the artificial neural networks. They are nonlinear maps that take some input and let's like variable y0 here, and they map it to some output variable yl. In its simplest form, the way that they're organized is as cascade of linear transitions and followed by element-wise nonlinearity. So some terminologies, we refer to this linear transition matrix weight or synaptic weight, and we call these outputs basically at each layer activations. So we said that these are nonlinear maps, and usually these synaptic weights are randomly initialized, and given a particular task, we want to optimize these parameters in order to basically for this to do particular mapping that we want. For example, let's say this data is a data set of dogs and images of dogs and cats, and we want to take this and we want to, given each image, map them to its correct label. So then we will basically have our data set, images of dogs and cats, and the corresponding ground truth label. So at first, these weights are randomly initialized, but when we have, so we need to optimize this basically weights. The way to do that is that we pass some image to it, and then we get the prediction corresponding to that. And then we have the ground truth in our data set. We compare the basically ground truth with the prediction of our network using some loss function, and that gives us the deviation of our output from what we are expecting it to be. And when basically we have here loss landscape, we navigate through this loss landscape starting from the initial weights to get to the region where we essentially minimize loss function. Usually we talk about this in the context of maximization, so we can say maximizing the negative loss. So most approaches that are basically practical approaches for this are gradient based, meaning that they use a gradient of this loss function here to navigate through this loss landscape. And the reason for that is that the gradient of loss is showing the direction for the steepest ascent in the negative loss landscape. So in modern deep learning, the most prevalent approach for computing these gradients efficiently is called backpropagation. To summarize this easily, I'm going to show the computational graph of the network, meaning that this is a directed graph. Each variable is shown with a node here, and let's say that I have my input y0 and I have my base w01 here. I have, so these two arrows show a basically operation, now matrix multiplication here. I get z bar, I then apply another function on it, and so on and so forth until I get my output and I compute loss based off of that. So this shows how different variables depend on each other. So based upon this, I can represent the gradients that I want, gradients of the loss function, basically loss with respect to different rates, synaptic rates in the network. And based upon this, I can use the calculus chain rule to basically expand this derivation. So I can write dl over dw as dl over dz times dz over dw to 3. And then I can repeat that for everything else. I can say dl over dz2 times dz2 over dw12 is going to be the derivative of loss with respect to weight 1, 2. Now, the second term as an analytical solution based off of our forward equation, but the first term we refer to as modulating signal or teaching signal that we're using to tweak the weights. Now, if you compare it with the previous one, you see that the error term for the previous layer, upstream layer, and remember, we compute L, you're going backward from the last layer. So the error for the second layer included the error for this upstream layer as well. So I can rewrite this error for layer 2 as basically as a function of the error in this upstream layer. And when we write this down, in summary, we see that error in each upstream layer is computed by propagating the errors in the downstream layer backward through weights that are transpose of the forward connection. And we can see that more clearly here. So we can think about it as a network being a forward pathway, propagating information forward, and then we get a loss, and then we compute some error based off of this loss, and then we are using an auxiliary backward pathway to propagate these errors backward toward the upstream layers, and we are using weights that are exact transpose of the forward connections. Now, after populating all these errors here, we use multiplication of the error term, postsynaptic error terms and presynaptic activations in order to update our synaptic weight here. Now, we call that a basically plasticity rule. That's essentially our delta W that we add basically to update our weight at each iteration. Now, in neuroscience, many researchers are trying to model the domains of intelligence using these deep learning models. But the problem is these basically backpropagation approach is not biologically plausible. And what it means is that if we consider that there's a backprop-like algorithm going on in the brain, that means that there is a forward path that takes basically input, some sensory input, information that your mind takes in, and propagate this until it gets some output. And there is some exact symmetric network that brings the errors backward from basically that output. So that means that there are two sets of symmetric essentially weights in your brain, that one is propagating information forward, one is bringing you back errors. But there is no evidence of existence of such symmetric basically networks in your brain. Now, there has been a ton of research to show that learning is still possible without this symmetry constraint. Now, for example, many of the older basically older approaches have some tie to the forward weight. So they're saying that instead of exactly using the transpose of the forward weight in the backward basically pathway, what we do is that we discard the magnitude of these, but we keep the sign. So we have a sign symmetry in order to support learning in these neural networks. But in a more radical approach, a group from DeepMind came up with the idea that we can just use matrices that are fixed throughout training. They are not changing. Matrices that are sampled from some random distribution. and have no ties with the forward weights. And they show that learning is still possible if we don't have symmetry there. Now, the question is, how well these are performing? Well, for smaller networks that don't have too many layers, for networks that have lower dimension of their activations, and for the ones that don't have any nonlinearities, the performances were similar to backpropagation. But as we add these basically complexities to our network, it becomes worse and worse. So for example, here I have a 3-layer neural network, and I'm training it on a 10-class classification on MNIST data, which is just handwritten digits 1 to 3 until 9. So for randomly, so it's a 10-class classification. If we randomly select, it's gonna be a 10% chance that we are selecting the true thing. So at first you see that it's starting from our baseline is 10. Now 10%. Now for this, the difference is not much. But as I add layers to my network, here I have a 5-layer neural network, I see that the performance of feedback alignment method that is using fixed feedbacks to train the model is way worse than the backpropagation. And the differences between backpropagation and feedback alignment in the performance here are 2 things. First of all, it's a slow learner, meaning that for the first 1,500 data points that I'm showing to this network, it's not even learning anything. And the second one is that even after learning, after converging, the performance is lower than backpropagation. It's 20% below what backpropagation is giving us. Now, just note that in all the tests that I'm showing, I'm training the networks online, meaning that I'm showing the data points one by single to my training, basically to my model, because that is more brain-like. That's how basically our brains are being trained. We're being shown data points one at a time. We are not getting basically a batch of data at once. So, and I'm just basically showing one time and one time only. So it doesn't see the data. It doesn't have, multiple epochs. And that's a harsher, basically, training condition. So now to illustrate what's happening, we have on top our backpropagation, on bottom our feedback alignment. We see that in backpropagation, we have this loss landscape. We start from some random initialization of our weight. We use the direction of the gradient to navigate the negative loss landscape, and it takes us smoothly toward the region that we maximizes negative loss. But in feedback alignment, for the first part, it's not learning. So it's not even getting close to where we want it to be. And then after it starts to learn, it doesn't quite get us where we want it to get. Now, here on the second plot, what you see is the deviation of the error signals of the backpropagation and feedback alignment. So I'm measuring the angle that my feedback alignment error signals have with what basically backprop has. So that means that essentially how backprop-like my feedback alignment method is. It's a high-dimensional space. These activation basically errors are high-dimensional. And based off of that, it's like the 90-degree here shows that it's I'm randomly initializing their orthogonal. And then as soon as it becomes less than 90, meaning that the error signals of feedback alignment start to be more backprop-like, we start to learn here. So that's essentially the idea for feedback alignment. Now, so learning happens essentially as soon as the error signals become more backprop-like. Now we see that this direction was not good. The ideas in this basically work that I'm presenting is that we put this aside, we find a new direction F that is guiding us through this loss landscape. And given that we're hoping to get a performance that is essentially learning fast at the beginning in the low data regime, and the performance, the overall performance, it basically improves upon the feedback alignment. And doing so, we see that
the alignment angles, essentially the error signals of the new plasticity rule are more backdrop-like, coming down to 20 degrees. Now, what we're using to find this learning direction is called meta-learning. Now, what is meta-learning? In a regular training session, what we have is that you got a data set. Based off of that, you want to train your model. So you sample data from this data set, you pass it to your model, it gives you a prediction. You take that prediction based off of a loss function or some objective, you measure how well that prediction is, and that measure is given in a loss value, and that loss value you provide that to an optimizer, and this optimizer includes my plasticity rule, my learning steps essentially. So I get this to my optimizer and I update my model, and I repeat that until I go through all the data in my data set. And then in meta learning, I have an altered additional learning loop, optimization loop, where now I take the model that was trained in this basically inner loop, I evaluate this on a held out data set from the same data set that we trained on, but it didn't see this part of the data set. And we get the predictions. Now we have a meta objective that is not necessarily the same as objective. It depends on the problem that we are solving, what basically loss we want to use. And then we evaluate using this meta objective, how well some basically this model performed. And based off of that, we optimize some meta parameters. And these meta parameters now can be anything about the inner learning loop. So now here we want to learn plasticity rules. So we want to parameterize this plasticity rule inside optimizer. And in the meta optimization, we want to learn parameters for that plasticity rule. The inner loop I'm going to call, it is called adaptation. The outer loop is called meta optimization. And I'm not going to get into meta learning jargon, but the meta iteration loop is referred to as an episode. That's the only thing that I'm going to keep using in the rest of the talk. So when we learn these plasticity rules, we're essentially learning to learn. Now, to show that, to illustrate that, let's say that we have our network that we want to optimize. We want to basically train this network that we have. We have some parameterization of a plasticity rule that is guiding us through this loss landscape. We first initialize these hyperparameters, and then we basically navigate the loss landscape with that, and we get to somewhere that doesn't really have a good performance because the plasticity rule was just randomly initialized, and it didn't basically perform well. Now, this value is the initial value for our meta parameters, and based off of the performance that the model showed in the adaptation loop, using meta loss, I find basically the gradient of meta loss, and I now navigate through this meta loss landscape. And then I get a new meta parameter, updated meta parameter, pass it up to my parameterized learning rule, and now it's basically able to better navigate through the loss landscape. And I repeat that until I get a basically set of meta parameters that give us a plasticity rule that can essentially efficiently guide us through the loss landscape and is efficiently able to train our models. Now, note that I'm showing the same basically W0 across different episodes, but that doesn't really, that is not really the case, because if I do that, I'm gonna condition my learned plasticity rule on a particular initialization of the network, and I'm at each basically adaptation I'm gonna randomly initialize the network. And I'm just showing this because I want to illustrate how basically plasticity rule is basically improving at each episode. Now, now the question is, well, we need a parameterization of this plasticity rule. How can we basically come up with this parameterization? For that, I'm gonna look at the underlying mechanism of my actual problem, feedback alignment, and to see what can possibly improve this. So in feedback alignment, model is trained using backward connections that are fixed throughout the training. So the idea is that in this type of setting, the weights evolve themselves to be transposed like of the backward connections. For that to happen, information from back, so W should somehow learn about essentially this fixed feedbacks that we have in the backward connection. So we should see trace how information are flowing from B32 to, for example, B23. So first we have, let's say that we have propagated our information, we found the loss, we found the derivative of that, and now we have the error in the last layer. We propagate that backward through this fixed feedbacks, and we get error in its upstream layer. Now let's say that we have populated all these through the same equation, and now we want to update our synaptic weight. We update them using a combination of this postsynaptic errors and presynaptic activations. And we multiply those, add them to this weight here. Now information from B32 got to W12. In the next forward propagation of information, they get to Y2. And then in the next update, they're gonna be added to W23. So we see that in 2 iterations, information from B32 got to W23. So now when we compare back propagation with feedback alignment, the only difference that essentially interrupts the flow of information is that these backward connections are fixed. Otherwise, forward connections in a given iteration are the same basically for feedback alignment. When we start from a basically given iteration, at first these things are same, right? So because of that, all activations are the same. Loss is going to be the same. The error in the last layer is going to be same. So based off of that, the problem starts when we get to this fixed feedback connections. And we want to propagate this E3 backward. We hypothesize that if we come up with new combinations of the local basically errors and activations, meaning that pre and postsynaptic errors and pre and postsynaptic activations, this would be able to improve the flow of information in our network during training, and hence it would be able to improve the performance of the model. Now, so based on that, we essentially use different combinations of pre and postsynaptic errors and activations, and come up with a set of candidate plasticity rules. And then we parameterize our model as a linear combinations of these candidate plasticity rules. We initialize this, we use that to navigate through the loss landscape. Then we see what our performance is. We use that performance to navigate through the meta loss landscape. And then we update our meta parameters, pass that to our plasticity, parameterized plasticity rule, and use that again to navigate through the loss landscape. And we repeat that until we converge basically to some basically optimized data. Now, what candidate rules did we use? Well, we started with quadratic combinations of errors and activations. You might notice this term, which is the same gradient term, and or I will call this pseudo gradient because in feedback alignment, it's not gonna give you the exact gradient, right? So this term, and then this other term is known in basically as Hebbian plasticity rule, which is a biologically inspired plasticity rule. But when we use this, we realize that this will result in our weights to grow and eventually blow up. So it will introduce unstable dynamics to our problem, and we have substituted that with Oya's rule, which is a basically constrained version of Pavian rule that has this constraint that doesn't allow the weights to blow up. Next, we tried some higher order terms to see maybe if these quadratic terms didn't work, maybe higher order terms will be able to bring back the flow of information in the training process. And lastly, we added a decatur, weight decatur, because we wanted to make sure that our model is actually learning. It's not overfitting, meaning that it's not just summarizing the training data that it's seeing. Now, if the hyperparameter corresponding to this plasticity rule is anything but 0, it means that the model sees that there is some overfit and there's some need to weight decay. All right, so let's say that this worked and we had a nice plasticity rule that we can improve the learning with. Well, what we want to do is not just use it for this problem. We want to be able to take that plasticity rule, identify it, and be able to generalize that to other basically types of layers or other types of networks. For that, we need to be able to interpret this. And we have taken some measures to be able to do so. First of all, we're using metaparameter sharing, meaning that all synaptic weights in the network are being updated using the same plasticity rule. The other thing is that so the pool of candidates plasticity terms can include tens of plasticity rules. It can have 20, 30, whatever. For that reason, it's really hard to study 20 basically different candidate terms after our model basically found some hyperparameter for each of them. So what we want to do is to suppress the insignificant ones. And insignificant ones means that the ones that have flat landscape doesn't really improve anything. The ones that have low efficiency, meaning that they're improving something, but they're so expensive, for instance, that we are better off without those. And the overlapping mechanism, meaning that there are multiple terms that are using the same underlying mechanism in order to basically improve learning. And we only want to study the most dominant one. We don't want to basically put time and effort on studying every single one of them. In order to do so, we have introduced a basically L1 penalization in order to promote sparsity within our hyperparameter space, and in order to have a measure of feature selection so that we select which one of these plasticity terms is more dominant. Now, before testing the candidate plasticity terms, what we want to do is to see how our meta-learner works on backpropagation and how it works on feedback alignment, to kind of benchmark these two and to see essentially, well, if we're improving upon feedback alignment and how far we are from backpropagation. So that means that I have used this plasticity term. It's the same term that both backprop and feedback alignment are using. The only difference between feedback alignment has errors that are updated using fixed feedback connections. And this guy over here, our learning rate, is the only metaparameter that we have. So this is the plasticity term that is going to guide us through the loss landscape. We start with some random initialization for our network. And this is going to direct us through the loss landscape. And then we see that, well, after however many iterations that we have designated, we get to some Wn, and we mark the performance of that Wn at the end of that episode. And based on this performance, I update my metaparameter. I update it, I get a new value, I pass it here, I take it, and again, use it to see how well I can optimize my network. And then I repeat that until I basically get to, our metaparameter converges. So over here, you can see the evolution of the meta parameters in 600 episodes, and you can see the basically meta accuracy in 600 episodes. Each accuracy that you see is marked only at the end of each episode. So we don't show the evolution through a single episode, meaning that we don't show the evolution through the adaptation loop. And we repeat the same thing for the backpropagation. Now, we have now benchmarked both performances. The problem that we're solving here is a 5-class classification problem, meaning that now 20% performance is our baseline. We see that our feedback alignment method shows a 25% accuracy, and our backpropagation method shows a 70% accuracy. So this is just improving 5% amount, basically from the baseline. And that means that feedback alignment is a slow learner, meaning that given the number of iterations in the adaptation, it only can get to 25% accuracy. Now, you might say that backpropagation is basically should be able to easily get to 100% for a 5-class classification. Why is it at 70%? Because at each iteration, we are only using 250 data points in order to train our model. That means that and we're again using online training, it only sees those data points one time and one time only. So because of that, that's a pretty hard training setting. And because of that, the even backpropagation can't get more than 70%. And if we look at the alignment angles between the error signals of feedback alignment and backpropagation, we see that they're around 85 degrees. So it's not backprop-like at all, essentially. Not at all, but relatively not backprop-like. So now we use our candidate plasticity terms as their tool to parameterize the plasticity rule, and we test using meta learning, and we see that we can improve, in fact, the performance of our model, both you can see it in accuracy and loss plot. So the moment that in the 10th episode, our performance crossed that of the feedback alignments, it shows that our model has discovered some plasticity term out of our candidate plasticity pool that improves improves upon feedback alignment. And what that means is that our hypothesis was correct, that one of these plasticity terms will eventually help us to improve upon feedback alignment. Now, again, we look at how backprop-like their error signals are, and we see that now the error signals come down to 60 degrees, so more backprop-like error signals using the learned plasticity rule. And here we see the evolution of the meta parameters. Now, if you look here, you see that because of the regularization term that we introduced, our model was able to suppress the insignificant plasticity terms, and only 3 dominant terms are standing out. And those 3 include first the basically pseudogradient term that both backpropagation and feedback alignment are using. Then what we call error-based Hebbian style term, because it is like the Hebbian term, it's pre and post-synaptic. Basically variables multiplied with each other, but it's on the backward connection. So we refer to that as EHEB essentially. And then there is OYAS rule. Now we want to see, are these 3 really the ones that are improving our performance? So we discard all other things, and then we repeat the test with just combination of these 3, and we call that FBio. Meaning biologically plausible plasticity rule that we discovered. And we see that in fact the performance is backprop-like, but I'm using this discovered plasticity rule, both in loss and accuracy. And I see that our angles comes down to around 35 degrees. Now, Well, okay, we were able to identify out of a pool of plasticity terms, two terms that are helping us to improve. Now, what we want to do is to study these and be able to see how these are participating in the improvement, enhancement in the accuracy. Well, we start from the error-based heading term. What we do is that each time we only add one of these auxiliary terms that we have discovered to the pseudo-gradient term, and again, take a look at the performance to see if basically how basically that differs from all three of them together. Well, we see here that the alignment angles are even better when I'm using only error-based heading term. I set aside the OEA's rule. On the other hand, I see that the performance is not as well as the one that I see with three of them all together. So there are two takeaway messages here. The first one is that this EHEP term is the driving force behind our learning becoming more backdrop-like, because now these error signals are even more backdrop-like than three of them together. So this guy is responsible for our signals being more backdrop-like. But from the accuracy, we can see that, well, not everything is becoming more backdrop-like. Now, intuitively, how this works is that we said in feedback alignment, we want the forward weights. The forward weights will evolve themselves to become the transpose-like of the backward connection. And that was happening in two steps in a flow of information like this, using this first term. In the second term that we have introduced, first error basically is being computed after forward propagation, and then this is propagated backward to compute the error in the upstream layer. And the combination of these two is going to be used to update our weight. That means that this E2 contains information about B32. This is directly being added to this. So this is pushing essentially, this is introducing an auxiliary channel to communicate between W and B. And this is happening at the same iteration, unlike the first term that was happening in two iterations. That means that this is going to improve with the speed of learning to become faster. Now, we were able to show this analytically as well. We see that the expectation of this EHEP term is proportional to the transpose of B under some basically assumptions. And these assumptions are, for example, if B is sampled from a random distribution centered on 0, which is what all other networks are using, and if they're sampled IID, and also we were basically able to show this when the network is linear. But we believe that the same thing is happening in the networks that basically have added nonlinearities in the forward path. Other thing is that we want to be comprehensive. We want to use the same plasticity rules for all weights. This term means pre and post-synaptic plasticity, but there is no presynaptic plasticity in the first layer. So we introduce a synthetic error, which we compute by backpropagating the error in the last layer through some fixed random connection. Now we can also show this experimentally. In this test, first I'm using the basically feedback alignment to update all layers. And then I'm gonna see how adding EHEP to each of these update rules for different layers is gonna affect the alignment of the angle of each of these errors with their backprop counterpart. First, I'm basically training with feedback alignment. I see that the alignment angle for this E1 is 76, for E2 is 82. When I add EHEP to all of these three terms, I see they drop to 28 degrees for the E2, and it drops to 49 for E1. Now, I don't introduce EHEP to last one, and I see that it's still the same, essentially, angles. Now, next, I again only apply it to last layer. I see that last layer's alignment is still the same, but the first layer, alpha 1, is not basically seeing any improvement, right? Now, I only apply it to W1, 2. This time I see that there is some improvement in alpha 1. It's not as much as when we had it, had added in the downstream layer as well, but it's still basically a substantial improvement. So adding EHEB to this W is gonna affect the, result in the presynaptic error to become more backdrop-like. That's what's happening basically with EHEB. And now again, we see that while I did not introduce that to W23, alpha 2 is still seeing some substantial 10-degree improvement. And that's because the flow of improvement in the flow information in the forward path is going to still result in some improvement in the downstream error signals. And one last thing, you see that alpha 1 again, we said that it's not as good as before. Before when I added to both, it was coming down to 49, now it's just 59. That's because, well, E1 is computed by propagating E2 backward. Now that E2 does not have that added to its plasticity rule, that means that E1 is not gonna have basically the full benefits of EHEB. So last term that we wanted to study was Oya's rule. So we set up a basically test where we use meta-learning to essentially meta-optimize the hyperparameters for this plasticity rule. And we see that the performance of Oya's rule is good. 3 of them together was better, but Oya's rule is good. But what's surprising is that there is no significant improvement in the alignment angles when we are adding this Oya's rule here. And well, we were under impression that improvement in accuracy is going to happen only when we have more backdrop-like signals, but that's not that much of the case here. But still, the improvement in the accuracy is substantial. But if we think about it, we see that the error, this term here involves only pre and post synaptic activations and the current state of the synaptic weight. So meaning that it does not have any error terms in it. So therefore, it's only reasonable to not expect this term to affect the alignment angles of the error signals. Now, the takeaway from this is that this rule is trying to circumvent our basically backward propagation of information, and it wants to implement some sort of unsupervised learning in order to improve our learning. Well, how is that happening? You have Oya's rule alone, which is a combination of a Hessian rule and some orthonormality constraint. Now, when I have a basically network that is trained on purely Oya's rule, what's happening is that this algorithm is implementing a recursive nonlinear principal component analysis. And that means is if I take my weight, synaptic weight W, the rows of this synaptic weight are going to construct orthonormal bases, and then they're going to span the same subspace as the principal directions of our input activation. But we're not here using pure Oya's rule to train our model. We're adding this to the network's basically own plasticity rule. Now the question is adding this alone trying to basically make rows of the weight matrix to become more orthonormal-like? And for that, there is an error measure, which is an approximation because we have nonlinearities. The actual basically computing how orthonormal like these is intractable. So we use this error measure to see how close they are to a stable solution of Euler's rule. Essentially, these rows being orthonormal. And we see that when we are using Euler's rule, there is a significant difference between how much these basically rows of weight matrix are close to orthonormal basis. Now, well, okay, we agree with that, but how this possibly can result in an improvement in the performance? Well, we can think about the classifier as having two phases. In the first phase, we have a feature extractor. We have some input. By passing it through the forward path, we're extracting feature representations out of the image. And we have the last layer, which is kind of a predictor, takes this feature representations and map them to the correct category that input image belongs to. Now, if these layers have basically weights that have basically more orthonormal rows, what's happening is that the correlation between these is decreasing. What's happening is that each layer is providing increasingly more discriminative feature representations. So now we are able to better distinguish between different images. Now that happens, the last layer, the predictor, has an easier time to do its predictions because it's provided with a better quality set of feature representations. All right, so conclusion. Feedback line backpropagation is the dominant approach to train deep neural networks, but that states that we should have symmetric backward connections in order to be able to learn, which is not biologically plausible. There are other approaches that show that it's still possible to learn without this symmetric constraint, but the performance of those models is not as good. So what happens is that we are saying that, well, we want to take the same constraints that are defined in those approaches and improve the plasticity rule to see if we can improve the learning process, the performance of the model at the end of learning. And we see that that's possible. And what method we use is meta-learning, which is a machine learning paradigm that has basically essentially two-loop optimization. In the inner loop, you just learn a task. In the outer loop, you're learning something about the inner loop. And that something here is the coefficients of the plasticity term. Now, we wanted to be able to take this and generalize this to other approaches, other basically layers. So we wanted to study particular term that was resulting in improvement. So we took two measures. First, we use metaparameter sharing, meaning that I'm using the same exact parameterized plasticity rule to update every synaptic weight in our network. And then again, I'm using L1 penalty to regularize my meta loss so that I suppress the plasticity terms that are insignificant, so that the dominant ones stand out, and I can spend my basically time only studying those that are dominant. Doing so, we discovered two plasticity rules. One was two plasticity rules to improve feedback alignment. One of them was called EF plasticity term, which we called it, and how it helps is by making the error signals become more backprop-like. That means that at best, that can perform as well as backpropagation. So its performance is capped by backpropagation. Then we saw that Euler's rule is also helping, and trying to understand how that's helping, we realized that it's not trying to make the learning process more backprop-like. So its performance is not capped with backpropagation, and it can surpass that. And we in fact saw that in some cases, for the models that are not properly initialized, adding Euler's rule is going to improve even training using backpropagation. So in this particular study, we were studying the particular case where forward connections and backward connections were not symmetric. Well, and in this particular case, we were looking at the scenario that backward weights were not being updated. Now, this can be used for other scenarios as well. This meta-learning framework can be extended to other basically scenarios. For example, the backward connections can also exhibit plasticity in biological entities. So we can use this to learn a plasticity rule again for the backward connections as well. Again, we only use this to learn parameters of the plasticity rules, but we can also parameterize other core components of a deep learning model and meta-learn those basically components. For example, we can parameterize model architecture, or we can parameterize objective function in order to meta-learn them. So for instance, in objective function, you can parameterize some objective functions so that our model learns without a need for data or with need for less data, some sort of semi-supervised or basically unsupervised learning. And the other thing that basically we can do with this is that here we introduce some biological constraints, have basically training online, not having the symmetric weights, but there are other biological constraints that we can introduce. For example, we can have neural recordings from some primate's brain and then use that as our biological constraints in the outer loop to learn models in the inner loop that are performing more like biological basically models. So thank you so much for listening. I'll take any questions, and this is essentially the results of our work is published here, hopefully coming up in next couple weeks. Thank you so much.